All right, chapter 6, working some more with our trig functions, except this unit deals with the trig identities and using the different identities to prove whether a statement is true or false. So we're going to start with reciprocal, quotient, and the Pythagorean identities. Some of this is a little bit new, but a lot of it is just building on what you already know about the trig identities. So first of all, let's start with our basic trig identities. We know we have sine, cos, and tangent. Those are our basic identities. Then we dealt with our reciprocal identities. And the reciprocal identities, if you remember from last time, those were cosecant, secant, cotangent, and tangent. So sorry, not tangent. I'm doing something else with that. Cosecant x then is the reciprocal function of 1 over sine. Secant x is the same as 1 over cos. Cotangent is the equivalent of 1 over tangent x. And remember, when we were doing these are called the reciprocal identities and not inverse. The inverse is when we do that, and we're trying to find out what the value of theta would be given a number. So tangent x, if you remember from last unit, is also the same. If you think of Sir Kicks or Ticks, it's the y over the x, and we know from our unit circle that y is the same as the sine function, and cos is the same as the x coordinate, not function. So then that means that cotangent, if we're thinking of it in terms of sine and cos, is the reciprocal of the tangent function. So that means this would be cos x over sine x. So these are the basic reciprocal identities that we're going to be using when we're working with some of our proofs. So it says practice with complex fractions, simplify and state the restrictions. So I have cos x over sine x divided by sine x over cos x. So first of all, to simplify this is the exact same as saying cos x over sine x divided by sine x over cos x. So using just our solving when we're dividing with fractions, that means we have to multiply by the reciprocal. Cos x over sine x times cos x over sine x. So this then, if we multiply it through, would be the same as cos squared x over sine squared x. And if you remember from last unit 2, or 2 units ago, I'm not even sure, cos squared x is the same as saying cos x squared, which is the same as saying cos x all squared. Those all equal each other. Cos squared over x squared, if you think of cos over x, that's the same as cotangent. So that would mean, completely simplified, this is the same as saying cotangent squared x. Now this one says to simplify and then state the restrictions. The best way to remember, if you've done all of the restrictions, is anytime you see a bar, okay, or a divide sign, you need to have a restriction. So take, for example, in this first one, I have a bar here, so that means this is a denominator. And then because of this bar in between, because of this bar, okay, so anything under the bar has to have a denominator. So there's a bar, I have to, or not a denominator, has to have a restriction. There's a bar, so this has to have a restriction. There's a bar, so I need to do a restriction for that one as well. Okay, so like I said, simplest way to remember that is whenever you see a bar, you have to have a restriction. So that means what we have to do is we have to put whatever these denominators are not equal to 0. So I have to have sine x is not equal to 0. And sine of x is not equal to 0. Well, and I'll do cos x at the same time. And cos x is not equal to 0. So that means x cannot equal, and because these are dealing with zeros, then we know we're using the unit circle. So we have 0, sorry, 1, 0. I always mix that one up. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So sine x is equal to 0 here, so at 0 and 2 pi. Sine x is also equal 0 at pi. Cos x then is equal to 0 at 90, so at pi over 2 and 3 pi over 2. So you should do this at all as 1. So here is our solution. Our restrictions then, because those were all of the places that they were. So if you look at this, we had 0, 2 pi, pi over 2, 3 pi over 2. So, and then that means every time we went around. So every time we went around back to 2 pi or back to pi, we're going to have a restriction. So that'll work if we say for every pi times n, we will have a restriction. So pi times 0 would mean we'd be starting right at 0. Pi times 1 means that would be that 180. Pi times 2 would be the 360. So our restriction simplified would be pi times n, and restriction is also then at every pi over 2, 3 pi over 2. So then they'd be back again at this here. If we go back around, it's going to be 5 pi over 2, and then 7 pi over 2, and then it keeps going around and around. So this would be pi over 2 plus pi n. So every 90 degrees plus a 180 turn, or a pi turn. So then those are our restrictions in general form. Because unless the question stated between, like for this one, I could have just wrote those if I had a restriction like this. What did it use? It used x. Then those would be all my restrictions. Because there was no limitations on there or no boundaries on there, then I have to write it in general terms. Okay, so let's do the next one. Tangent x divided by secant x over cosecant x. So the best thing to always do is write this without that initial bar. So this is the same as tangent x divided by secant x over cosecant x. So this is tangent x times multiplied by the reciprocal. Now I know that tangent x is, or sorry, not tangent x, cosecant x is the same as 1 over sine x, which means if that's 1 over sine x, that means I'm dividing it by secant x, which is the one same as 1 over cos x. So if I write this all out, tangent x, since I'm working in terms of sine and cosine, I might as well change this tangent into sine and cos terms. So tangent, if you remember, was the same as sine over cos. So this is sine x over cos x times 1 over sine x times cos x over 1. So I was dividing by it, so I multiply by the reciprocal. So now I see, okay, what can I reduce? So my sine x and sine x will reduce, and my cos x and my cos x will reduce. So I'm left with 1. So that is my solution to this one. So now if I want to do my restrictions, I know I've got secant x cannot equal to 0, and cosecant x cannot equal 0. So secant x is the same as 1 over cos x not equaling 0. And we know from over here, cos x can't be 0 at that 90 degrees, and then 90 and then 270, or pi over 2, 3 pi over 2, and all the way around. So this one will be at x is not equal to pi over 2 plus pi n, so every 90 degrees plus a rotation, or plus a half rotation. Secant x is the same as 1 over sine of x. And we know from the last question that, or just even from the unit circle, that that's every pi. That starting at 0, every pi is going to be a restriction. So this one is x is not equal to pi n. And the one thing I didn't write on both of these is that n is an element of integers, right? You're always multiplying by that whole either positive or negative number. So there's your restrictions, and there is your solution of 1. Okay, next one says simplify and state the restrictions. So same idea. Cotangent x divided by cosecant x times cosine x. So the first thing that we want to do then is let's write these so that they're all in terms of, since we've got cosines in there and we can work with cosine and sine in here, we're going to change them so that they're all in cosine terms. So cotangent x is the same as cos x over sine x. This is divided by 1 over cosecant is 1 over sine x times cos x. So if I rewrite with my my flip, what I'm going to do is, because this is together, this is the same as saying cos x over sine x divided by cos x over sine x. Whoops, I put a 6 there instead of a sine x. So if I just multiply this through, so now when I do my multiply by the reciprocal, so sine x over cos x, and I do my cancels, cos and cos, sine and sine, so this equals 1. So I need to restate my restrictions. So since this cosecant x, cosine x is the same as this, then those are my two restrictions that I'm working with. Cos x can equal 0, and I could leave it as cosecant, it would be the same thing. Because then it just changes to 1 over sine, but you can go straight from where you've changed that into the cosine term. So cos x is not equal to 0, sine x is not equal to 0, so I know that my restrictions are at pi n. X is not equal to pi times n. I was going to write a sign in between there. And then it is, so that's for sine. For cosine, it's not equal to pi over 2 plus pi n. And again, these are elements of real numbers. So those are your restrictions, and there's your solution. Okay, secant x, tangent x. Secant x is the same as 1 over cos x. Tangent x, we know, is the same as, whoops, not sine. Oh, yeah, sorry, I have that right. Sine over cosine. So I know my restrictions there. Once I have done my flip, I'll know my restrictions. So I have 1 over cos x times cos x over sin x. So cos x, I should have used a different color. Cos x and cos x cancel, so this is 1 over sin x, which is the same as cosecant x. So my restrictions is everything under the bar, and that bar is the equivalent of the divide sign, so everything after the divide sign, so that means the same thing. I have sin x is not equal to 0, and excuse me, cos x is not equal to 0. So sin x then, again, is that x is not equal to pi n, so every pi that you hit, and then x is not equal to, for cosecant, pi over 2 plus pi n. So you start at the 90 degrees and then you go a half turn after that. So there's our restrictions, and there's our solution. And it's not a bad idea to circle those, because once you start doing ones where you've got a few more steps in them, it gets confusing as to what was the answer and what wasn't the answer, what was just part of the solution. Okay, so this one says simplify and state the restrictions, verify with a graphing calculator this time. Okay, so we're going to do the same thing. You always want to write them in terms of sine and cos, so this is the same as saying sin x times 1 over cos x. So sin x over cos x is the same. That's just tangent x. So the only thing underneath a bar or underneath a divide sign was that cos x. So your restriction, cos x can equal to 0, so x is not equal to, well, I wrote this in the opposite order, but pi over 2 plus pi n. So there's our restriction, and there's our solution, and let's check on a graphing calculator. Maybe. There it is. Okay. So our original equation was sin x times secant x. Oops. So I need my functions here. So I do sin x times, what is it? Secant x. Secant x. And there you go, you can see you have a tangent graph, and my zoom is a little wild, so that's even worse. So anyway, you can see that it made a tangent graph, so I know I'm right. Okay, so let's try the next one. Tangent x cosine x divided by sin x. So this is the same as saying tangent is sin x over cos x times cos x, and this is being divided by sin x. So I have sin x divided by cos x times cos x times 1 over sin x. My cancels, cos and a sine and a sine. So I'm left with 1. So I take a look, okay, what all was underneath a bar or behind a divide sign? So that means that this cos x and this. So my restrictions, cos x is not equal to 0, so x is not equal to pi over 2 plus pi n, and then sin x not equal to 0, so x is not equal to pi n. And those are elements of integers. So there was, whoops, my two solutions, or my solution and my restriction. Cosecant x divided by cotangent x. So cosecant is the same as 1 over sin x divided by cotangent is the same as, whoops, cos x over sine x. Best way to remember this, it's a cotangent, so the cosine has to be on top. So I have 1 over sine x times sine x over cos x. So if I do my cancel, sine and sine, so this is 1 over cosecant x, which is the same as secant x. So that is my solution. Now, if I'm looking for what was underneath or behind a restriction, so I had my sine x, and this sine x and cos x were both behind the restrictions, but I don't need to do the sine x twice, so I have sine x is not equal to 0, cos x is not equal to 0, so x is not equal to, pi n, and x is not equal to pi over 2 plus pi n. Okay, so now we're going to do more, but we're going to throw in a couple of operations in there. So I have 1 plus sine x cos x divided by cos x. So what we want to do with this is we want to break up this fraction. So this is the same as saying 1 over cos x plus sine x cos x over cos x. So 1 over cos x plus sine x cos x all over cos x. So once you've broken it up, then do whatever canceling and simplifying you can. So I can't do anything here, and I can't, and this is where you have to be careful. I can't go cos x and cos x because this is a plus sign in between. If it was a multiply, I could do that. But because it's not a multiply, I can't. So that means this 1 over cos x, nothing I can do with it this second, but I can go between my sine x, cos x divided by cos x, and cross those off. So 1 over cos x is the same as secant x. Plus, that left me with sine x. So that is my simplified solution there. Restrictions. What was underneath a, and this one didn't ask for restrictions, but if it did, what's underneath is that cos x, so I'd have to do that one. Alright, cos squared x plus sine x divided by sine x over cos x. So same thing, I have to write them each as their own part instead of all together under one denominator. So cos squared x cos x plus sine x over sine x cos x. So now I can reduce. My cos x will take away one of those cos x's. My sine x and my sine x will cancel. So I have cos x over sine x plus 1 over cos x. So that reduces or simplifies further. Cos x over sine x is cotangent x, and 1 over cosecant x is the same as secant x. So that is solved. Restrictions, I would have had to use the sine and the cos. So we can go from just simplifying these to actually finding values for them when you are given actual measurements instead of just x's or theta or whatever variable. So to calculate the following, I have sine squared pi over 3 plus cos squared pi over 3. So pi over 3, I know or should know by now, comes with a special identity of its own. It's part of that 30, 60, 90 triangle. So pi over 3, if I draw this, if this is pi over 3, then that means my sides are going to be if that's the 60 side. So this is going to be my square root 3, my hypotenuse is 2, and that pi over 6 side is a 1. So now if I do my calculation here, this is the same as saying sine of pi over 3. So pi over 3 is opposite over hypotenuse. So this is square root 3 over 2 all squared. Sorry. Plus cos squared pi over 3. So pi over 3 cos is adjacent over hypotenuse. So that's 1/2 all squared. So this is the same as saying 3 over 4 plus 1 over 4. So my answer is just 1. Just going to write in my pi over 6. Okay, so now the next one. 2 pi over 3 plus cos squared 2 pi over 3. So when I'm doing them, I have to still think of my castrals. This one, because it was just a pi over 3, I know it's in that first quadrant, so everything's going to be positive. I didn't have to worry about signs in there. But when I'm doing other equations that aren't within that first quadrant, or other angles, I mean, then I have to watch and see, okay, what quadrant is it in, and will that particular trig function be positive or negative there. So 2 pi over 3 is over in this quadrant. 2 pi over 3 means that I have to use a reference angle. So if this is my 2 pi over 3, that means that my reference angle is a pi over 3. So if my reference angle is pi over 3, then for sine, using cast rule, my sine will be positive there. So I'm going to have 2 pi over 3 sine of that. Well, it's the same as this one here, so it's square root 3 over 2 all squared plus cosine of 2 pi over 3. So cosine is 1 over 2, but cos is negative there, so I have to square that. So in this case, I will have 3 over 4 plus that negative 1 squared is the same as a positive 1/4, so my answer is still 1. Okay, we still deal with the unit circle. On this, you saw when we were finding our restrictions that we use the unit circle exclusively. So this says for any point on the unit circle xy, x squared plus y squared is equal to 1. So we talked about that last unit. In order for a point to be on a unit circle, when you square your coordinates, they have to equal to 1, because the radius of a unit circle is 1. So it says another thing that we learned about the unit circle is that x is equal to cos theta and y is equal to sine theta. So that's what we used when we were thinking the tangent y over x. So that's where that sine over cos came from. It says if we combine the two, we get what is known as a Pythagorean identity. So instead of saying x's here and y's, if we substitute in knowing that on the unit circle x is cos and y is sine, we get the Pythagorean identity from this formula. So this is the same as saying cos squared theta plus sine squared theta is equal to 1. Or it can also be written, instead of thetas there, you could have cos squared x plus sine squared x equals, or sine squared x equals 1. Okay, and these can be reversed. You could also say sine squared theta plus cos squared theta is equal to 1. That's that additive property that you would have done way, way, way back in grade 3 or 4. So from that basic Pythagorean identity, we can manipulate it so that we can get some other identities. So it says from this we can divide both sides by sine squared x and cos squared x to get two other identities. So cos squared x plus sine squared x or theta, if we divide we're going to do it twice. First, we're going to divide everything by sine, and then we're going to divide everything by cos. So if I start with first this, cos squared x plus sine squared x, and I divide, both sides by sine x. This one leaves me with, sorry, not sine x, sine squared x. Cos squared x over sine squared x is the same as cotangent squared x. Sine squared x over sine squared x, those will just cancel and leave me with 1. Cos squared x plus sine squared x is equal to 1, so if I put that over sine squared x, 1 over sine squared x is the same as cosecant squared x. So that is one manipulation of the Pythagorean identity, and usually the way we write it is 1 plus, you put the 1 first, cotangent squared x is equal to cosecant squared x. So let's try it the other way. Let's try it with dividing cos squared into both of these. So sine squared theta divided by cos squared theta plus cos squared theta divided by cos squared theta is equal to 1 over cos squared theta. So you can see I'm interchanging my thetas and my coses, and I used, for the first one I use the cos sine, and then this one I use the sine cos. It doesn't matter. It'll still give you the same thing because you're only switching them within the equation. You're not switching them over the equation. So sine squared cos squared is the same as sine over cos is tangent squared theta. Cos squared divided by cos squared is 1. 1 over cos squared is the same as secant squared. Oops, better stick with theta. So this identity then is 1 plus tangent squared theta is equal to secant squared theta. Now on your departmental exam, just something for you to take note of. They give you the basic trig identities to deal with these. I'm just trying to find a copy. So they give you the reciprocal identities. So cosecant theta is equal to 1 over sine, and the rest of those. They give you the basic Pythagorean 1 of sine squared plus cos squared theta is equal to 1, and they do give you these two, 1 plus tangent squared and the 1 plus cotangent squared. So you don't need to memorize them, but it's a good idea to become really familiar with them so that you don't always have to keep flipping back and forth to refer to them. Okay, so let's do some proofs. This is the best part of this whole math course, proving. So we're going to use these identities that we know in order to prove these triangles. So far we have the reciprocal identities, and we have this the Pythagorean identities. Ooh, can't even speak anymore. And then we also did the quotient identities on the other page. So cosecant squared theta plus sine squared theta plus tangent squared theta is equal to secant squared theta. As soon as you see that this is a proof, what we want to do is we want to prove that our left side is equal to our right side. So that means we're going to do our chart, okay, our t-chart. So our left side. Oops, I probably shouldn't make it quite so big so I'm not running into that guy. So left side, and then my right side. So cosecant squared theta plus sine squared theta. Well, right away, you should be able to recognize that as being the same as your tangent. Cosecant squared plus sine squared theta. That is your, what's this called? Pythagorean identity. I said tangent because I'm going to tangent. But I also know that that is the same as saying if I hang on. I just think I just wrote something down. Sorry, pause. Okay, sorry. Sorry about that. I thought I'd made a mistake in writing something down here, but it's right the way it is. So cosine squared theta plus sine squared theta, from that Pythagorean identity we know is the same as saying 1. So that is the same as saying 1 plus tangent squared theta, and on the right side of the equation we have that secant squared theta. 1 plus tangent squared theta. Well, according to our manipulated Pythagorean identity, 1 plus tangent squared theta is the equivalent of secant squared theta, which means my left side is equal to my right side. So I'm right. And we write, once you finish the proof, and you might remember this from doing a little bit of proofs last year, or can't remember when we did proofs, that QID, which is just Latin for proven as asked for or something, I can't remember. But anyway, QID. So our next one here, I'm just going to put a line. 1 minus cosine squared theta, sorry, cos squared x, tan squared x is equal to cos squared x. So 1 minus cos squared x, tan squared x. Well, there's no identity in here, and because there is not a plus sign in here or anything in between, I can't really say 1 minus cos squared is equal to sine squared, because that would just be changing this one, right? I can move anything around here. I can say sine squared theta is equal to 1 minus cos squared theta. Okay, but because this is being multiplied to it, I can't just pull that out. So this is all one term, is what I was trying to get there. I can't just pull out that 1 minus cos squared x there. So if I set up my left side and my right side, 1 minus cos squared, can't do anything with that, but I know that tangent squared is the same as sine x over cos x. So because this is still one term, so it's the same as this was here, just rewritten in terms of sine and cos, I can cancel. I can go cos x and take out one of these, and that leaves me with 1 cos x. Sorry, this is a squared too. Boy, I wish I could get my variables right. So this and this cancel out completely. So what I'm left with is 1 minus sine squared x. This was cos squared x on this side. 1 minus sine squared x. So just like I was saying, up here, I can manipulate these equations however I want just by moving them across that equal sign. So sine squared theta is the same as 1 minus cos squared theta, which means that cos squared theta is the same as, if I bring that over, 1 minus sine squared theta. So I haven't changed anything in my equation. I've just moved something from one side of the equation to the other. So 1 minus sine squared theta is the same as cos squared theta, which means left side is equal to right side, and we proved what we needed to prove. Okay, then the last one here. Sin x minus cosecant x is equal to negative cotangent x cos x. Okay, so left side and my right side. And remember, I always want to write these when I can in terms of just sine and cos. So sine x is fine. 1 minus cosecant x is the same as 1 over sine x. On this side, negative cotangent x is the same as saying negative cos x over sine x, and then times cos x. So if I want this to have a common denominator over here, sine x and 1 minus sine x, that means I would have to take this sine x and multiply it by 1 over sine x. Okay, multiply the top and bottom, whatever in order. I said by 1, but it should be sine x over sine x. So whatever I do to the top, I have to do to the bottom. So this becomes sine squared x minus 1, and now these will both be over a denominator of sine x. So all I've done is I've taken my sine x times 1 times sine x over sine x, so that's sine squared x over sine x, and this already was 1 minus sine x. So they have a common denominator. I can put them over 1. On this side here, on the right side, I have 1 minus cos x times cos x, so that's negative cos squared x over sine x. Sine squared x minus 1. Well, I know that 1 minus sine squared x is the same as cos x. So what I've done is I've just taken my equation again, I'll write it down here. Cos squared theta minus, or plus sine squared theta is equal to 1. So what I've done, what I can do, is if I move this over here and that over there, I have sine squared theta minus 1 is equal to negative cos squared theta. So I've just moved from the left side to the right side to the left side. So sine squared theta is the same as 1 minus cos squared, x over sine x. And on this side, I already have negative cos squared x over sine x. So left side is equal to right side. Proved what I needed to prove. So those are all your examples for this section, and there are your questions. Have fun.